Okay. Um, so I have, well, here it is. This is a fun assignment. Um, so I should say that the homeworks that we are going to have this week and next week, they get progressively harder and harder. I know I don't want to discourage you, but there are, um, but part of the difficulty is that you're starting to learn how to interpret and the probability statements, and because sometimes you just don't know what they're even asking. And eventually, we're going to get to the point where you're going to be able to say, oh, this is just like that. Like there's a whole bunch of different types of probabilities that are like dealing cards. And so if we can master the dealing cards, you can master the other things. And they're like, oh, this is just like flipping coins. And you'll be like, oh, yeah, this is easy. So, but it just takes a while to get used to this. So hopefully you can be patient for the process. And I'm going to be patient this week because there's not a lot of new material. We're going to sort of ease into this stuff. So I've got the homework. At least this is what. And oh, and by the way, I'm looking to get a copy of the international version so that I can look at both of them. Still don't have one, but it seems that you guys all got the cheapos. I can get one for $25, which seems like a pretty good deal. So I just haven't pulled the trigger yet, but I will. I'll get it, and that way we can all enjoy both versions. But this is the American version, so I'll do my best to make the conversion to the international version. But for either one, where do we need to focus? You know, sometimes it's just getting over the hump of trying to understand the structure of what's going on. Yeah, what do you think, Sarah? Number 18. But can I just read mine? Well, yeah, let me just, we can compare real quick. Yeah, we're not playing with cards. You're not playing with cards? No. Okay, well, I'm really curious. Yeah, go ahead, read it. There's a lot of words, so I'll speak slowly. Okay. So you can get all this information. Okay, tell. Each of 20 families selected to take part in a treasure hunt consists of a mother, father, son, and daughter. 20 families. Mother, father, son, daughter. Okay. Assuming that they look for the treasure in pairs that are randomly chosen from the 80 participating individuals, and that each pair has the same probability of finding the treasure, calculate the probability that the pair that finds the treasure includes a mother but not her daughter. Finding. Okay, finding. What in the world? Yeah, I need to get a copy of this book because this is not at all like what I have. Okay, let's think through this for a minute. So I guess this is a good illustration of what we're doing this chapter, and what I'm hoping that you learn from this chapter is that the first thing to do is to try to understand the problem. So I think I understand, but I think I'm going to have to just spend another minute in just a sec. We'll talk through this one more time to understand. Then try to choose, like, what are the theorems? What are the axioms? What is it? What are the rules that we're going to use to? That's where I'm not seeing it immediately. So if we're all in the same boat here, but let's see if we can. Let me make sure that I understand what this question is asking, because wow, that one, this is so much different. Okay, so you have 20 families. That means 80 people. I know it said that, but let's see, people. They're all like this. And we want to know the probability. Okay, the probability that the pair, so a mother finds the treasure without her daughter, without her daughter. Oh man. Okay, so I got to go way down here. Let's see. So let me just sketch this out real quick. Let's see. So you have M1, M2, M3 up to, why is there 20? Okay, and then father 1, father 2, etc. So I'm just naming the people now. Son 1, son 2, etc. down to son 20. And then daughter 1, daughter 2, daughter 20. Man, the ones that I picked were so much better than this. Okay. It's going to be all right. Okay, so here's the sort of the tableau. They've got all these 80 people. And so first off, let's see. I want to know the probability that mother sub I is on the team that finds the treasure and is not paired with not with daughter I. Okay, so okay, so let's see. Yeah, I don't know how to do this without using techniques that we haven't learned yet. Um, I'm thinking through. So let's just review the theorems real quick, the important ones. So you have the basics, but I'd say that the important. So here are what I would consider the important theorems. So number one is the number one superstar theorem, and that is that the probability of the complement of an event is 1 minus the probability of the event. Let's see, can I apply that here? What if I put the mother and the daughter together and have them find the treasure?
What I tried was and complement.
Yeah, well, that's what I was thinking. Is if we can do some sort of a complement, that might do it.
Because it would include the mother and exclude the daughter. That's what I was thinking.
Oh, I see. Like this. MIDI complement.
Yeah, that's what I tried.
Okay. So wait. So we have MI is going to be mother one. Mother MI is mother I finds the treasure, and then D sub I is daughter I. Wow, this one is hard. Okay. Okay, well let me get the theorems down, and then this may be one that I have to take with me. Yeah, I think that it's an emergency. I must buy a copy of this book. So I'll do it right today or maybe tomorrow morning. But I'll get myself a copy of the international version. That way I can prevent this sort of thing. At least I can look at them and say, no. So, okay, it's going to be all right. So the next one is this. A union B is the probability of A plus the probability of B minus the probability of AB. That's the inclusion-exclusion principle. This does feel more like an intersection, not a union. Although I was trying to think, could I do a complement, use this with an intersection, which turns it into a union using De Morgan's law. Let's see, number three really is a subset of number two, so I'm not even going to write it down. So let's just stick with these two as our main theorems. And yeah, this one is very frustrating. This is frustrating to me that it's so different. Yeah, because the one, so just let's back up. Let me make myself feel at least a little better about my life. Here it is, number 18, yeah. So two cards, this one is just what's the probability of getting blackjack? And so I'm using this theorem. It's the sub-theorem, if you will. It's really the axiom. You have two mutually exclusive events. One of them is get an ace, then a 10. The other one is get a 10, then an ace. And by 10, I should put that in quotes. It's one of these cards, a card that's worth 10. So, I mean, that's an easy thing to compute because you're just going to add these two probabilities together. Why did I put probabilities there? There. So this is going to be, yeah, you'll add them together. Yeah, on the fly here, I'm not seeing it obvious. It's not obvious to me. So I don't want to flounder here and not be able to do it. But I guess I'll take this as my homework now, if you don't mind. Let's just a sec. Let's see. So this is the probability. What if we do this? The probability that mother I, daughter I, and then we could do 1 minus this. Oh, but we want mother I to be on the team, but not be with daughter I. Yeah, see, this would be a relatively easy, well, relatively speaking, easy thing to do if I could use some techniques that we're going to learn later on. Right. Yeah, so let's save this. I'll keep this as like that. Because what you want to do is you want to know, first of all, what's the probability that mother I is on the team, and then you want to get rid of daughter I. but to do that sequentially is the way I would do it, not all in one like I think that they want us to do it. So I'll try to figure it out, but I'll just save that for later if that's okay. That's this week. Whew. Okay. Well, what else? Any American versions that we can do? I got them. I did those. All right. What do you got for the Americans? Yeah, USA, USA. Okay. Sorry. Okay. Okay. So this one's not bad. So here it is. And I'm curious, is this similar to the what? See, this is why I'm gonna have to get myself a copy of that book so that I can look, decide which ones are the same, and just assign those. Because this one's not bad. So, um, so 7 balls randomly drawn from an urn. I have an urn in my office. If you really want to see it, it looks like a vase. A vase is an urn, okay? But anyway, 12 red, 16 blue, and 18 green. So I want to know the probability. So we'll go through these all. I know that you probably aren't having trouble with all of them, but just for completeness, A is pretty straightforward. You're going to have, let's see, 20, let's see, 18, 30, 46. Is that right? 46 balls, and you're choosing 7 of them. And you want to know the probability of getting 3 red. So out of 12, I need 3 of them to be red. I want, out of the blues, I want 2 blues, and I want 18, choose 2 greens. So I'm just choosing these things sequentially. So I choose 3 of the reds, choose 2 of the blues, choose 2 of the greens. And that'll give me the probability. So A isn't bad. It's just a counting issue. And so you might have had a little trouble figuring out the counting on the numerator, but you're going to get really used to this sort of notation. You're going to say, oh yeah, there are a lot of things that we do probabilistically that look like this. So anyway, you'll become really familiar with that sort of notation. The next one, letter B. Letter B, at least 2 red balls are withdrawn. I just have a few notes here just in case I forget what I'm doing, just to remind me how I did it. But I figured it's pretty easy. So with letter B, I'm going to do 1 minus the probability of either 0 red, or 1 red. So that's what I'm trying to write there. So at least 2 means not 0 and not 1. So now we could just do the rest of this. Is pretty straightforward as well. So 1 minus, let's make a big set of parentheses here. So 0 red means all of the balls are either blue or green. And what is the total here? There are a total of 16 plus 18, which is 34? 34. So there are 34 green or blue, and I'm going to choose 7 of them. Divide that by 46, choose 7. So this is the probability of having no reds. Notice that you're getting all of your balls from the blues and greens, and then this is because probability is a comparison of what could happen with what did happen, or yeah, what you want to happen, I guess. And then this is going to, how many ways can you have 1 red? Well, there are 12 red balls, so you pick one of those, or better yet, just so that it looks the same as all the rest, you're going to choose one of your 12 red balls to be the reds, and then of the other 34 balls, you don't care what colors you get, just as long as you get 6 of them that are not red. This is over 46, choose 7. So there's that complementary principle here, 1 minus the opposite. And so I did the opposite. The opposite of getting 2 or more would be 0 or 1. So just 1 minus that. And this is still foreign. It's okay that you're thinking, this is part of why I'm sort of planned both mentally and also with what I'm assigning with this going slowly this week, is because I know that we're going to need to get used to this sort of language and this sort of thinking. So stop me though if there's a question or if you think something's a little awry with any of this. And we could actually compute these numbers, but I'm more interested in making sure that you understand where the number, like I could write this as a decimal, but that's not going to help you. This, hopefully, you can read this and understand you're doing 1 minus, and then here's 0 reds, and here's 1 red. That's 2 or more will be the opposite of that. Okay, so let's do C and D. So these, once again, these are all so happy, compared to that families of 4 people and 80 people walking around. No idea. Okay, all of the balls are the same color. So this is the mutually exclusive situation. So I'm just going to do it this way. 7 red plus the probability of getting 7 blue plus the probability of getting 7 green. So just to explain briefly, let's just, yeah, well, I'll just do it this way. That what we're really interested in is this: 7 red or 7 blue or 7 green. I guess I need to label these. This is going to be set A or set B or event A or B or C. We'll just name them that just to show you how this works. So this is going to be A union B union C. Whenever you're doing this, or when you're talking about events, if all you care about is either this or that happening, then it's a union. And then having all 7 of the balls be blue is mutually exclusive of having them all red. And so we can use the simplified version of the probability of a union, A union B union C, that says that you just drop the unions and add up the probabilities. So that is pretty easy. I mean, I could finish it, but I mean, here it's going to be 12 choose 7 over 40. What was it? 46 choose 7. That's the, oh, darn. Try again. 46 choose 7 plus 18 choose 7 over 46 choose 7 plus 16 choose 7. I think I got those right. 46 choose 7. So yeah, so you're just adding those probabilities together because you're dealing with unions of things that are mutually exclusive. And then the final one is actually, I think, the easiest. I misread that when I wrote this. Ignore this. That's not right. Okay, either exactly 3 red balls or exactly 3 blue balls. Okay. But not both. Either or, but not both. Do you interpret that as not both? Not both. Okay, so it's either this or that, but not both. Because you could have both happen. So I guess what we will do, let's see. There, I'm going to write this out just to illustrate. Let's see, go down here all the way. So let's set, or event A is the event that you have exactly 3 red. Event B is going to be exactly 3 blue. So what I'm really interested in, I'm going to write this. I want the probability of A, B complement unioned with A complement B. So I'm just double checking. Is that correct? Because that would be exactly 3 red, but not exactly 3 blue. And then exactly 3 blue, but not exactly 3 red. And I don't like the way that this is going to, let me just see if this is going to be a problem to compute. I think it will. A, B complement plus the probability of A complement B minus the intersection A, B complement A complement B. That's mutually exclusive, is it not? So this is the empty set. Yeah. Because if you have the A intersected with A complement, that's the empty set. So we'll get rid of this. We don't need all that. But then this is the problem that I think is going to be difficult. AB complement. So you want it to be 3 red, not 3 blue, not exactly 3 blue. So, so I think that I want to rewrite the question just slightly, or rewrite the way I'm going to do it. Why don't I do it this way? Let's see if this makes sense. What if I do the probability of A union B minus intersection? I think that does it. You know, it might be helpful to use a Venn diagram here, but um, yeah, I think that might be the best. Let's do the Venn diagram. No, let's not. Sorry, I just juked you there. You might be able to use a Venn diagram. Let's just go ahead and do this the way that it's written here, because that's really the way it's written. So we'll suffer through. It's okay. I can do it. It's just that it's going to be a lot of work, and I don't like work. Okay. So probability of A intersected with B complement is you want 3 reds. So that's 12 choose. I'll just do this first one, because if you can do this one will be similar. So if you can understand the first one, the second one will be similar. So you want 3 reds, and you either want 0, 1, 2, or 4 blues. So that's what it means. B complement, B is exactly 3 blue. So you either want 0, 1, oh, so could I do exactly 3 and do the complement? I think I could. Choose 3, let me see. Will that work? Just a minute. Because that's exactly 3 is easy. Let me try that. The probability of A, B complement is equal to the probability of A minus the probability of AB. Did we have that as a theorem? I feel like that's a theorem. We can pretend. I'm pretty sure it might have been on my PowerPoint and I just didn't get to it. So let's make that as one of our theorems. It's related to the complement. You can kind of see it looks like the complement. It's just that you have this A here instead of, so it's the complement. Here, I'll do it Venn diagram. I'll Venn diagram this one for sure. So here's A, here's B. And so here is AB complement right there is in green. And then here is A. A is everything inside this circle, but then you subtract the stuff inside this circle right here. So the light green, lime green is this, that is this, and that is this stuff. So you can kind of see visually that it makes sense that if you take this minus this, you get that. Okay, yeah, let's do it that way. That'll be the easier way. And then we can call it a day, hopefully. No, like I said, I was assuming that this would be a slow process this week, so we can take our time. Okay, so let's do it this way. The probability of A, that's 12 choose 3 times 18. No, not 18. How many more are there? 12 choose 3. Sorry, I got to go back to the original. 18 and 16, 34. 34 choose 4. So that's over 46 choose 7. So that's the probability of A. But then I'm going to subtract off the probability of, 12 choose 3. And then 18 choose 3. And 16 choose 1. So this is the probability that you get both A and B happening. That's 46 choose 7. So this will be, that looks great to me. I love it. This will be the answer to this. There are other ways to do it that are more laborious, but make more sense. So if it really doesn't make sense, I can do it the harder way. But this one is the easier way. And then this will be a similar situation. You can do probability of B minus the probability of AB. It's a similar deal to get that. And then add those together. And then hopefully it will match up the back of the book if there is a back of the book with this. So, all right, was there other stuff that you're dying to know about that's on, I would hope they would be on both versions of the book, but if not, I'll do my best with that international version, but I will order one so that I have a copy. Wow, no one's yelling. Well, here we'll do um, I guess I'll give you this quiz, which is all easy versions, I hope. Let me see. Oh, so easy, at least compared to all of that. These, especially those kids. So maybe I can do the families. I'll think about it while you're doing this. This one's super easy. Hopefully. I shouldn't say that because when I say it's easy, then people say, why are way harder? No, this one is a killer. One of the hardest quizzes you're going to have. So, yeah, keep your expectations extremely high. And those. There you go. Enjoy. This for me, I love it. Give me something to do. I'll come back for the rest, don't worry. Let me just do this for Audrey so that she can enjoy this herself. Okay, there. All right. Homework. Okay. Oh, we'll do it for Wednesday. Fine. It's better than nothing. Well, this one needs to be. Yeah, you need to do more. Yeah, do it for Wednesday. Oh, you did the wrong one. All right, yeah. No, Wednesday is good. We got to take our time with this stuff. Mm-hmm. Okay. Let's see. Yes, I knew it. 26. Okay. I just want to make sure that the wording is. Boy. All right, if you're finishing up, hopefully you're coming down the home stretch here. Uh, get my quiz back up here. Finally, I got 18 at least. I got the same answer that they have in the back of the book, so I can explain that. that. So yeah, if you are ready with your quiz, send it over. If you're not quite ready, yeah, you can then diagram it. Do you have an extra one you didn't want to do twice? So I'll do that. All right, you all set? Oh, yeah. Well, yeah. One more. Good enough. Thank you. All right, let me just, I'll make a quick notation, then I'll get the last one or two here. Let's see. Probability, peanut complement, coconut complement, nougat complement. There we go. Okay. All right. As good as it's going to get. So let's see how we do. I got them all? I just want to be sure. Okay, so let's see how this goes. Let's see, turn, what do I need to do? I need to do this to unfreeze. There we go. Okay, so you have all this information. Feels similar to, well, I don't know. Were there problems like this on your homework? Because there sure were with the American version. How about so was there stuff sort of like this on that version? Where they gave you a list of different attributes? There wasn't? One or two? Like, here's what, yeah, this I definitely need to, where's this? I guess that all of these, like this stuff, I don't know if you had this language class thing, where the cigarettes and the cigars was sort of similar. The language class was a good example, similar to this, because you have three different attributes. Either you're in German, French, or Spanish. Let's see, the Jack and Queen, the balls isn't quite the same. That's not quite the same. So, 21. Yeah. All right. Well, let's see how we did. So here's what it's asking for. You want no peanuts because you're allergic, no coconut because you hate coconut, and no nougat because you don't even know what that is. And so we want to know what's the probability that you don't get any of those. It doesn't contain peanuts, doesn't contain, so you've got an intersection here. So probably the easiest way to do this is to do 1 minus the probability of PC complement unioned. No, I'm sorry, is that? Yeah. Unioned with, no. Sorry. 1 minus the probability of P union with C, union with nougat there. Because P complement, C complement in complement is the same as P union C union in complement. So using the De Morgan's law thing turns unions into intersections. So you could do it this way, and then this is going to require you to use the inclusion-exclusion principle. I did it a little easier way, using a Venn diagram. So here's what my Venn diagram looks like. So you have peanuts, nougat, coconut, and the very last thing that they said was that all of the bars that contain peanuts and coconut also contain nougat. In other words, there was nothing, no bars that would fit into that category there. Coconut, peanuts, but not nougat. So that would be a 0. I guess I just obliterated my 0. So that means that the 22% that were in the peanut coconut category, they all had to be in the middle there. And then you can work your way outward. So basically, you're using the complement principle, saying that okay, if it's in the nougat and coconut, if those intersection, that was 26%, then you've already got 22% here, so you must have another 4% there. Anyway, so this is just a way that I could do it quicker than having to go through all the rigmarole of the inclusion-exclusion principle. And when I got done, I figured out that there were 26% that were outside all of the circles. Those are the candy bars that have none of the bad stuff, I guess, if these are bad. So So there's that. Hopefully that's not too bad. I guess I'll find out here in a bit when I grade this. This one was hopefully super easy, I hope, because this is the straightforward complements, the superstar theorem. So you're just going to say, okay, Saturday it's this, Sunday is this. I want to do the weekdays. It's just 1 minus the Saturdays and the Sundays. And that gives me, if I've done that was mental arithmetic. So can't trust me too far, but hopefully that's right. All right, maybe, maybe not. Okay, let's take a look at this number 18 again, since I finally figured it out. I've done my job already. So give me a sec here. I'll pull this up here. Let me explain what I did. Okay, how about this? I'll just redo it so we can talk through it. So just to remind you, we want to know what's the probability that on the winning team you have a mother and not her daughter. Okay, so what I had to do is I had to think through, okay, what does it mean for like mother one? So we're going to say M1 is mother one is on the winning team. Whatever that means. You find the treasure. It's such a bizarre problem. But mother one, that's M sub one. M sub two is mother two, etc. So D1 is daughter one is on the team. D2 is daughter 2, D3 is daughter 3, and so on. So there's my notation. Then what I'll do is I'll start computing probabilities, and I started simple. So we'll start with mother 1. What's the probability that mother 1 is on the team? Don't worry about daughter 1. I just want to understand the problem. So mother 1, well, first of all, there are 80 choose 2 teams. That's how many teams there are. And the probability that mother one is on the team that wins is 1 times, let's see, how many different, so this is the number of ways of picking the winning team. And now you need to pick a partner for mother one. Oops, not 2, it's 79 choose 1. So that's going to be 79 over 80 choose 2, and 80 choose 2, let's just give, this number is going to pop up over and over again. So this is going to be 3160. Okay, so that's the probability that mother 1 is on the winning team. Similarly, the probability that mother 2 is on the winning team is the same. In fact, the probability that mother I, whichever I is, so you pick a number, whoops, 79. I don't know why that turned into a 77. So that's the probability. You pick a mother, any mother. It could be your mother. The probability that any of the mothers is individually on the team with, who cares who they're with, is that going to be that number? There's, in a similar way, the probability of any of the individual daughters being on the team that wins will be the same. So this is just individually. Now let's go for a combo of mother one and daughter one. Wow, we're gonna be doing great. So how about mother one and daughter one? For them together to be on the winning team, well, that's just one way out of 31. Once again, that 3160 is just 80 choose 2. You're picking a winning team from your 80 people. You're picking 2 people to win. So the probability that the mother one, daughter one is on that winning team, there's only one way. It's for mother one and daughter one to be chosen and to get the prize. One way for it to happen out of 3160. Okay, we're almost ready. We have, and this, by the way, you could probably figure out that this is true for no matter what number. So if you pick mother 3 and daughter 3, mother 10 and daughter 10, so I'll just use M sub I and D sub I, also 1 out of 3160. So far, so good? Pause and make sure that you're not losing your mind too much. I mean, it's hard. This is hard. I mean, obviously, I had to take a breather before I could do this one, and because I had stage fright. It's hard to do it, especially in front of other people. So don't be down on yourself as you're learning this stuff if you're not getting it immediately. But through repetition, through doing this, hopefully you'll start seeing the patterns. But anyway, so far so good. We're just doing the simple cases, so the basics. Now let's get to what we're really interested in, and that is what is the probability that, let's see, the probability of, so here's how I did this. I guess um, how did I do it? Go back and check my work. Sorry. Uh, that's right. Mother one. That's it. That's it. Okay. So now let's go and think about what it means for you to have a mother, but not her daughter. Well, that means that you have to have the mother, 100%, but then she has 78 other people she could be with. So 78 out of 3160. So that's the probability of having a mother, a specific mother, like pick a mother, mother one, mother two, whichever one, for her and not her daughter. Okay, so now you might think, well, what we could do is we could just union these all together. Let's add them up. So I goes from 1 to 20 because there's 20 families. Mother I, daughter I complement. So that would be 20 times 78 over 3160. The only problem with that is that in doing that, you end up double counting, which is it's so hard to avoid. So you might say, who are you double counting? Well, here's the problem is, think about exactly how we're doing this. We're saying, I want to know the probability of having mother, let's just pick mother one to start out. Mother one and anyone other than her daughter. Well, anyone other than her daughter includes mother two. And then when we get to mother two, we say, I want to know the probability of having mother two and anyone other than her daughter. That includes mother one. And so we've double counted all of the double mothers. And so now I have to subtract off. So it's like the inclusion exclusion principle. So I have to subtract off. What do I subtract off? Just a minute. Sorry. Still hard. It's hard. Okay, yeah. Yeah, that's how. Okay, so the final thing is I'm going to subtract off. I'll take this and I will subtract from it the probability of having two mothers, mi, mj, where I does not equal j. So I doesn't equal j. Okay, so let's just think how would we get two mothers, not the same number there? Well, you have 20 choices for your first mother and 19 choices for your second mother. So 20 times 19 over 3160. Sorry, that double counts as well because I could have mother one, mother two, or mother two, mother one. Oh, but that's okay because in this case, I've double counted each mother pair twice because I counted the mother. Oh, wait, but I want to only take off away one of them. Okay, so I don't want to. Here, I'll do it this way. Let's get rid of this. Let's do it right. It's 20 choose 2. That's it. That's the probability of having two mothers. That better? Okay, so then what you're going to do is you're going to take this number, subtract this number, and I did it earlier on a calculator, and I got the same number that was in the back of her book, so I assume it's right. Let me just double check that's what I did up here. This does not, this is 20 times 19. I have 20 times 19 there. Is there some reason why it should be 20 times 19 instead of 20 choose 2? Crud, it worked for me. Well, yeah, everyone wants to pack up and go now, so maybe I'll double check it. I'll have to double check this. Okay, so what's going on for Wednesday? Apparently what's going on for Wednesday is I'm going to be ordering a book. And in addition to that, there is some homework, but I have no idea. I mean, I know what it's in the American version, but I have no idea what it is in the international. Do your best. If it's incredible, like if it's like this one, then just know that you're going to give me some joy eventually, because this is, I love challenges like this. It's just frustrating that it's not the same as the American version. So do your best with the homework that's due Wednesday. This is the whole week. This is what we're doing this week, by the way. So nothing too new. Look, these guys are just dying to get in here. Yeah, get out of here so they can come in. I'm going to stop the recording in case you